Here we have a simple three-line program written in C. All we want to do is define an array of integers and print out the first integer to the console. We can run this program and look, it works just as we hoped. We can see that 5 is the first integer, and then we're taking the first element of, wait, that doesn't look right. This must be a typo, we can't index an array like this. Well, in C, these are actually the same. But why would anyone use this syntax? Why does it even exist? Let's take a look. If you're not familiar with C, we'll first have to talk about memory management. Let's imagine that this is the memory that your program uses. Each cell represents 1 byte, which is 8 bits. Whenever you initialize a variable, like x equals 5, we put that value into memory. This is the number 5 in binary. An integer is typically 4 bytes or 32 bits, so we use up 4 cells. We can do the same thing to represent other types of data like floats and characters. We'll cut off the initial 4 bits of each cell in the image because for all the examples, the 4 starting bits will always be 0. This means that we will only show the final 4 bits of each byte in the cell. Let's label each of the cells with a number between 0 and 7. We'll refer to these as the cell numbers or memory locations. Let's define a pointer y. The star indicates that y is a pointer. A pointer lets us store a cell number or memory location. We can assign the memory location of x to y by using the ampersand. Now y is a pointer to x. Y does not hold the value of x. It holds the cell number that corresponds to the beginning of x. Let's add more memory to our program. Our pointer to x stores the value 0 since x starts in cell 0. For a 64-bit program, a pointer is typically 64 bits, so we store the value 0 in binary over 8 cells. We can use operations like addition or subtraction to change y depending on the data type that we're pointing to. When we add 1 to y, the cell number stored in y changes from 0 to 4 because the integer is 4 bytes. This means the pointer should not end up pointing to a value in the middle of an integer. Let's return to the original value of y, which is cell 0. We can use this pointer to retrieve the value that is being pointed to with the star operator. So star y has a value of 5, which is the same as x. Now we know what a pointer does. It stores the location of another variable in memory. But why is this important? Let's make an array of integers called a with 2 elements. We can get an element of the array in the same way we would with a language like Python, a of 0, a of 1, and so on. What we're really doing is going to the first element of the array and moving some number of cells away. So for a of 1, we begin at the first element in the array and move over 1 element. This is because a is really just a pointer to the first element in the array. Because a is a pointer, we can use star of a to get the value that a is pointing to. This is the same as a of 0, which is 5. We can also write this way, since adding 0 to a is still a. Now, if we want to get the value of the second element, a of 1, we can use star of a plus 1. A plus 1 is just a pointer that points to the second element of the array, and the star operator takes the value at that pointer. Remember before, we said that when we add 1 to a pointer, we move over 4 bytes because that's the size of an integer. This leaves us at the starting cell of the next integer of the array. Now we see that there are 2 ways to get a value in the array. Here's where things get a little interesting. Since we can use this syntax, we can also use this syntax to access the same value, since 1 plus a is the same as a plus 1. The order of 1 and a is flipped, but the resulting addition is the same. A pointer to memory 4 bytes after a. Now for the moment we've all been waiting for. We can think of the a of 1 syntax being a reformatted version of the star of a plus 1. Both of these will have the same value. Since we're just reformatting the new pointer syntax into our more recognizable syntax, we can flip the 1 in a, which results of a of 1. We still end up with the same value. Let's see it in action. I created a small program in C to demonstrate the ways that we can access a value from an array. All I've done is import the standard library and use the main function to run some examples. First, we initialize the array with 2 integers from before. Then, we try each variation that we reviewed. Each of these integers should be the same value of 9. We then print each value to the console so that we can confirm that we get the expected value of 9 for each. When we run this, we can see that all 4 print statements have the expected value of 9, which means that they all access the same value in the array as we wanted. Now we can go back to the original example of a of 0. We now know that a is a number that represents a location in memory. We can rearrange a and 0 because the sum of a and zeros always results in the same pointer. And that's it. This is one of my favorite programming oddities, so I hope this video was informative and interesting. Thanks for watching.